All right, so I finished my general announcements. The short version, CFU 19 was passed back today. Students have a week to retake that. Homework 63 through 67, which was assigned last week, is due tomorrow since we didn't have school yesterday. Homework is being collected tomorrow, not today. We have 2 weeks left before spring break. Each week is going to end on an assessment. CFU 20 this Friday will be passed back Wednesday of next week. Students will have a limited window to retake that, Wednesday, Thursday, Friday of next week. And then the following week, the last week before spring break, that's when we'll be taking our test on this entire note packet, graphing polynomials. Students are encouraged to arrange with Mr. Fee or myself to take that test a day early if they don't expect to be here on Friday, April 11th, right before spring break. But rest assured, if you do not take that test before spring break, it will be the first thing you have to do when you come back from spring break. So I'd really recommend you don't put yourself in that position. All right, students were already given a couple minutes to complete the multiplication at the top, page 26. We're going to go right into a problem that is related to determining end behavior. This is kind of the thing that we started on Thursday and had practice with on Friday. All right, so number one says, if you were to multiply and distribute out the function of x equals x times x plus 3 times x minus 2, what would be the degree of the polynomial? And the hint is how many x's are there. So if I actually took the time to multiply this by everything, can anybody see what degree of x you're going to end up with? The third power. This is, by the way, what we call cubic. We'll get into that term on the next page. This is a third degree polynomial. Now, if you don't believe me, that's why I designed part B. We're going to go ahead and actually multiply and distribute out this term. Now, this is just my personal strategy. You don't have to do it this way, but I'm going to ignore the x in the beginning. I'm going to pretend like that x doesn't even exist. I'll wait until the end to deal with that, and I'm just going to multiply the other two terms, okay? So I'm going to do x times x and x times negative 2, 3 times x and 3 times negative 2, okay? And I'm just going to copy this x in the beginning after I do all this. So x times x is x squared, x times negative 2 is negative 2x, 3 times x is 3x, and 3 times negative 2 is negative 6. Now, that's what you get when you multiply x plus 3 and x minus 2. But please remember, we still have two other things to consider. Number one, I never even used the x in the beginning, so I can't forget that that's there. I'm going to add that x in the beginning because I haven't actually done anything with it yet. The other thing I need to do is combine those terms in the middle, the negative 2x and the positive 3x. Negative 2x plus 3x is just x. So what you really have here is x times x squared plus x minus 6. Now, to continue the distribution, I now need to do x times every single term in this parenthesis. So this turns into our final answer. X times x squared is x to the third. X times x is x squared. And x times negative 6 is negative 6x. This is our final answer. Okay, and by the way, this proves the degree is 3 because that is the highest exponent. Now, this relates to the thing that we started on Thursday and you all practiced when I was out on Friday with Mr. Fee. Yes, sir. Because we have x times x squared. So it's kind of like x times x times x, 3 x's. Okay? Now, the pattern of what we discussed last class, or the last couple classes last week, is if you have an even degree, going to do the same thing on both sides. Let me show you a couple quick examples. I'll keep it simple, okay? Let's say I graph the function x squared. That is an even degree polynomial. So I know right away it wants to do the same thing on the left as it does on the right. Now, all functions want to go up on the right, unless you flip them. So this one doesn't have a negative, it's just regular x squared. So I guarantee that's going to be going up on both sides. Now, I could make one of two changes to this. If I flip it, so if I put like a negative number in front of it, that's now, it's still even degree, so it still wants to do the same thing on both sides, but now it's been flipped, so it wants to go down on both sides. I'm summarizing for you all what you should remember from last week, okay, towards the end of last week. Now, if I, instead of adding that negative, let me switch it back to positive, so it wants to be the same on both sides. But if I switch this to an odd degree polynomial, like x to the third, odd degrees want to do the opposite thing on the other side. Now, don't get me wrong, it still wants to go up on the right, but now it's going to go down on the left. And if I had flipped it, if I had added in a little negative there, well, now it wants to do different things because it's an odd degree polynomial. It normally wants to go up on the right, but I flipped it. So now this one is going to be going down on the right, and it's going to be going up on the left. Because that's essentially a summary of what we talked about towards the end of last week. Now, if you remember that pattern, then you can determine the end behavior of this thing very quickly. It's a third degree polynomial. So it wants to do different things on the left and right. Now, does it want to go up on the right and down on the left, or down on the right and up on the left? That's kind of what you have to figure out. Okay. And the way you determine that is, remember, all functions want to go up on the right. That's like the standard, unless you flip them. And this hasn't been flipped. It doesn't say negative x to the third or negative 7x to the third. It has not been flipped. So it wants to go up on the right side, which is what all functions want to do, unless you add a negative in there somewhere. And because it's an odd degree polynomial, it's going to do the opposite on both sides. All right, so this is an example that basically summarizes and uses what we were talking about last week on Friday and Thursday. What we're going to do now is we're going to flip the page. I'm going to summarize that process. I'm going to add one new thing, and then we're just going to practice it. And again, the overall goal is, can you create a sketch of a graph without a calculator? Go ahead and turn the page, folks. Now, most of this is not new. In fact, I would say all of this is not new. And the next two lines, that the 0 that comes from a factor with an odd degree and an even degree, like this stuff, I'm going to need to show you a couple examples for that to make sense. Okay, so that's not actually something that you've seen before. Okay, but a lot of this we've already been working with. Okay, the degree of a polynomial is the function's highest exponent. So if you have like 7x to the 5th, well, then it's a degree 5 polynomial. If you have 3x to the 20th, well, then it's a 20 degree polynomial. Whatever the highest exponent is, that's the degree. Now, the leading coefficient, okay, this is a common word that's used in math classes with equations. The leading coefficient is the number with the term that has the highest exponent. So if you have an equation, let me just make up something crazy real quick. This one I'll be complicated with. Okay, if I do negative 7x to the 5th plus 6x to the 4th minus 3x to the 3rd plus 8x squared minus x plus 8. Okay, I try to make some ridiculously complicated equation. The highest degree is 5. Okay, the highest exponent is 5. So this is a degree 5 polynomial. The leading coefficient is negative 7. It's the number that's attached to the term with the highest exponent. Okay, so nothing new so far. But let me just be clear. I know what the end behavior of this thing is instantly. Instantly. It's an odd degree polynomial because it's degree 5. So I know it wants to do opposite things on the left and right. And because the leading coefficient is negative, I know that it's going to be going down on the right. All functions want to go up unless you flip them. So I know before even graphing this crazy looking equation, I guarantee you it's going down on the right and it's going up on the left. Okay, and that's kind of what I want you all to be able to do, to be able to look at an equation and instantly know what is it doing on the left, what is it doing on the right. Okay. Now, a function's 0 is the same as its x-intercept, also referred to as a root. I will admit, even I find this a little obnoxious. Why is it that we sometimes have multiple terms to refer to the exact same thing? Okay, 0, x-intercept, root, they all mean the same thing. Now, up to this point, anytime we wanted to solve for the 0, we had a way of doing it mentally that was pretty instantaneous. We are going to do that again today, so I'll show you exactly what I'm referring to in a moment. But the strategy, if you can't just do it instantly in your head, is to set the factor to 0 and solve for x. I'm going to model that for you all. So technically speaking, that last line that we just filled in, it's nothing new, but it refers to a strategy we've never really had to use before. Now, here's where we get to the part that I would imagine is probably going to be a little confusing until you actually see it. So don't expect these next two lines to make sense yet. A 0 that comes from a factor with an odd degree goes through the x-axis. A 0 that comes from a factor with an even degree only touches the x-axis. Again, those two things I'll need to show you examples of in order for that to make sense. We'll get those examples on the next page. End behavior describes the direction the graph goes. Left is as x goes to negative infinity. Right is as x goes to positive infinity. That's not new. We've been talking about that. Now, the nice thing, and I'm trying to simplify this as much as I can, there are really only three possible answers to left and right end behavior. When you're looking at a function and trying to decide, what is it doing on the left? What is it doing on the right? You basically have three options. It's either going to shoot down forever, so negative, it's going to shoot up forever, so positive infinity, or it's going to level off at some number. Very often that number is 0. That's the most common place for a function to level off on, but it can level off in any numbers. Now, we are going to be using certain terms for certain degree polynomials, okay? We have linear for first degree functions. If you just have like 3x plus 7, that's a line. That's a linear function. If you have an x squared term, that's quadratic. X to the third is cubic. And the last one I will expect you all to have memorized is x to the fourth is quartic. I will not expect you to have memorized quintic. Okay, it's just not common enough. Okay, we will be looking at functions that are first, second, third, fourth, and fifth degrees. Okay, and really we could use any other degree even higher if we really wanted to. Okay, the names I will expect you to be able to know are linear, quadratic, cubic, and quartic. I don't expect you to know quintic. In fact, if you go to your calculator, and I know you all don't have calculators today, but if I actually go to the calc features, it actually has linear regression for x functions. It has quadratic regression for x squared functions, cubic regression for x to the third functions, and quartic regression for x to the fourth functions. It actually has first, second, third, and fourth degree polynomials built in. Even the calculator doesn't bother going to the fifth degree. Okay? So now we're going to move to we're going to do 3 problems similar to this one. That's basically what we have left today. 3 problems like this. And our goal is summarized in the first 2 words, without a calculator. Okay? So this says, without a calculator, write the required characteristics for the polynomial function below, then use the information to sketch a graph of the polynomial function. Okay, the first thing that occurs to me is when I'm looking at x1 times x minus 3, if I were to multiply this out, and I'll write this in green because you all don't have to, but if we were to multiply this out, this is what we would get. And the reason I'm pointing this out is because I need you all to recognize that if you were to multiply that out, you would have x times x, which produces x squared. So I want you to be able to look at that and know this is a second degree quadratic function. Now, the reason that's important, and I'm jumping around here a little bit, is this is an even number. So if this is an even degree, that means your left and right end behaviors are exactly the same. Now, the other thing I'd like you to notice, and again, I know I'm skipping over that zeros and roots part for just a moment. The other thing I want you to realize is that you already know what the left and right end behavior is instantly. It's an even degree function, so it has to be the same. They're either both going up or they're both going down. And I don't see a negative on any of those x's. I don't see x times negative x or negative 2x times x. It's just x squared. It's a positive leading coefficient, which means this function does exactly what every function wants to do. It goes up on the right, and because it's an even degree, it goes up on the left as well. It does the same thing on both sides. So when I'm ready, I'm not going to do it yet, but when I'm ready to sketch this thing, I need to make sure it's going up on the left and up on the right. However it is that I draw it, it needs to be going up on both the left and right sides. Now we get to something that you all can already do in your heads, but I'm going to show you a strategy because there will be harder examples where you can't do them in your heads. Can anyone look at these factors, x plus 1 and x minus 3, and tell me where does this function hit the x-axis? I heard -1 and 3. So hopefully everyone can appreciate what Jordan did there. She switched the numbers in the parentheses. +1 became -1. So I can look at that and know this thing hits at +1. And she took the -3 and switched to +3. I can look at that and know that it hits at +3. And what I submit to you all, and again, this is the goal for today, you can create the sketch of a graph if you can figure out just where does it hit the x-axis? And what does it do in the ends? What does it do in the left and right ends? So I guarantee you this function is going to look something like this. That's the rough sketch. That's all I'm looking for. And by the way, I'm not looking for perfection. I'm not going to be grading you on your CFU this Friday. I'm not going to grade you if it's more like that or if it's more like this. Okay? I'm not going to be picky about that part because I'm saying this is a non-calculator task. What I'm going to be picky about is, do you have x-intercepts in the right spot? And do you have the right end behavior? That's what I'm looking for. Okay? Yes, sir. Okay, so the question that was just asked is, where did I get the -1 from? Now, let me show you this part, which is the part I skipped in the problem below. It said to solve for the 0, set each factor equal to 0, solve for x. So if you're not able to do what Jordan did, although I would say the whole room could do it, okay, here's how you can get the -1 and the 3. Take the factor x plus 1 and set it equal to 0. Take the other factor, x minus 3, and set it equal to 0. And now solve these equations for x. Okay? Now, the first equation, you're going to subtract 1 from both sides. And the second equation, you're going to add 3 to both sides. Now, on the left, you end up with x equals -1. So you can solve a factor, set a factor equal to 0, solve it for x, and that will tell you where the function hits the x-axis. Same thing here. When you add 3 to both sides, you get x equals 3. Now, I will admit, the examples we're going to do today probably won't feel like it's all that necessary, but we will start to see more complicated factors. So having this strategy, I think, is a good thing. Okay? All right. I want to be clear. This is the real goal for today. We're using things we've already been doing. We're using our ability to determine end behavior, our ability to determine factors, okay, solve factors. Goal is to create a sketch of a, okay, go ahead and turn the page, folks. All right, once again, you'll see those same 2 words. Okay, it says without graphing, write the required characteristics for the polynomial function below, then use the information to sketch a graph of the polynomial function. Okay, so first things first. If you imagine this thing, x plus 1 times x plus 1, because it's x plus 1 squared, and then how many x minus 3s do we have? What's the exponent? If there is no exponent, what is it implied to be? Not 0, 1. We have 1 copy of x minus 3. So there's technically an exponent of 1 there. So we have x minus 3 once. The reason I go through writing that out for you all is I want you to see that if we multiply this out, we're going to have an x times an x times an x. We are going to end up with a cubic function. It's degree 3. The name of a degree 3 function is cubic. Now, here's why that's critical. I know that this is an odd power or odd degree, which means these are going to be different. Okay, the end behaviors are going to be different. Now, the other thing I'm noticing is, again, there's no negative x. Okay, it's just x times x times x. So I'm going to end up with positive x to the third. So it hasn't been flipped in any weird way. This function, like all functions, is going to go up on the right side. But because it's an odd degree function, it's going to do the opposite thing on the left and right, which means on the left side, it's going to go down. So before I even draw this thing, I'm going to picture it's got to be going up on the right. It's got to be going down on the left. Like that's something I have to realize. Okay. Now I just saw Tao make kind of a nice little wave with her hand. It looked like she did something like this. Does that make sense? And that's exactly what this function is going to look like. Don't copy that one though, because that was just made up. Okay. I don't know if it's going to hit the x-axis here or here or here. Like I don't know where it's going to hit the x-axis. So I have to figure that out. Okay. So let me undo that. And this is why I'm going to take each root, x plus 1, set it equal to 0, x minus 3 equal to 0. And when you solve, you get x equals -1 and x equals +3. So -1 and positive 3. Now, if I asked you all to graph this right now, I imagine some folks are going to run into some difficulty, okay? And this is related to the one new thing that was in the notes on the top of the previous page. It was the thing that I said, this isn't really going to make sense until you see it. But let me show you, I'm going to struggle with this on purpose. So don't copy what I'm about to do, just watch, okay? If I start on the left, I know that it has to be going down on the left. So it's going to come up, shoot through this x-intercept, come back down, hit that x-intercept, and then, wait a second, I'm stuck down here. You see this? It's like, how do I go up on the right? The only way I can go up on the right is if I cross the x-axis again, but then I'm inventing an x-intercept. You can't do that. The only x-intercepts are -1 and positive 3. It doesn't hit the x-axis somewhere else. So this doesn't work. This is no good. Okay, what if I start over here? Okay, I know it's got to go up over here, so let me hit the x-axis and hit the x-axis, and now I'm stuck again. Like, how am I supposed to go down on the left? Like, I got to cross through the x-axis. I have to invent an x-intercept. This is not okay. Here's the part that's critical. If you look back at our previous notes, this was the one thing that I mentioned was kind of new that we hadn't really seen before. What it says is, if you have an odd degree factor, the graph cuts through the x-axis at that point. But here's the key. If it's an even degree factor, it only touches the x-axis. So watch this. Because this factor produced this 0, but it's an even power, it's a 2. What that means is, at that location, at -1, the function does not cross through. It's not positive on one side and negative on the other. No, wrong. It's going to touch the x-axis. It's going to bounce off at that point. It's going to bounce off at that point. Everybody got that? Because that 0 comes from an even degree factor. So here's how you draw this thing correctly. And this part you can now copy. It has to go down on the left. It has to bounce off of this point. It has to cut through that point and then shoot up. And again, the reason it is bouncing off of this point is because it has to be the same on both sides of that factor. The reason it is cutting through this point is because that came from an odd degree factor. So it has to be different on either side of that root. That's the bottom line. Okay? Now I want to show you one more example of this type of problem, and then, believe it or not, we'll be done. Okay, so let me show you what it's going to be really, really similar to this because it's going to have an even factor and an odd powered factor. So it'll have a point that it bounces off of, it'll have a point that it cuts through. Okay, here we go. Last problem of the day. So once again, without graphing, write the required characteristics for the polynomial function below, then use the information to sketch a graph of the polynomial function. So I'm imagining I have 2 copies of x minus 2. I have 1 copy of x plus 1. So if you multiply this out, you'll have x times x times x, which is cubic. Because that is an odd degree, the end behaviors are going to be different. One is going to be positive, one is going to be negative. So I'm already picturing this thing shoots down on the left, up on the right. Now I got to figure out what are the x-intercepts. So I'm going to take the first factor, x minus 2, set it to 0. Take the other factor, x plus 1, set it to 0. And I'm going to solve each of these for x. If you add 2 to both sides, you get x equals 2. You subtract 1 from both sides, you get x equals -1. So this thing is going to hit the x-axis at positive 2 and -1. And what's critical to realize is this is an even factor, which means it's going to bounce off of that point. It's not going to cut through it. It's going to bounce off of it. Okay. However, the other one, the -1, came from an odd factor. So at that location, it is going to cut through. So I need to draw a graph that goes up on the right, down on the left, cuts through -1, but bounces off of positive 2. And here's what that might look like. Down on the left, cut through -1, bounce off of positive 2, and then go up. And I can guarantee you, if I graph that, this is what it looks like. I'll prove it to you real quick. If I type x minus 2 squared times x plus 1, oh, what is that? Let me get rid of that. There we go. I guarantee you when I hit graph, it's going to look basically like that. It's going to be coming up, cut through -1, bounce off of 2, and then keep going. You can see, cut through -1, bounced off of +2, and then kept going up. That's the idea. And I want to stress, I am not going to mark you wrong if your graph looks like this. I'm not grading you on does your graph look perfect. I'm grading you on do you have the right x-intercepts and do you have the right end behavior. Okay. And, I'll also check, are you cutting through the point? Are you bouncing off the right point? That's what I'm looking for. I'm not looking for perfection. I'm looking for a reasonable drawing of what the graph would look like. Okay. All right. We're done. So at this point, folks, you have what you need to be able to complete homework number 68. Thanks for watching. Have a good one.